Sometimes when I'm computing a definite integral or the area under a curve, I don't really care about the exact answer, I just care about a good approximation. And one way to do that is with Riemann sums. Riemann sums are where I take the area I'm looking for and I approximate it by treating it as a bunch of rectangles. For instance, the sum of the areas of these four green rectangles will be approximately the blue area that I'm looking for. It's not exact, it's close enough. The question is, how tall should I make these rectangles to make my approximation a good approximation? In this video, I'm going to talk about what's called a left-hand Riemann approximation. A left Riemann approximation means each rectangle should line up with the function at its top left corner. For instance, between 0 and 1, I'm going to use the value of f of 0. I'm going to use the y value that goes with an x value of 0. Between 1 and 2, I use f of 1 as the height of my rectangle. Between 2 and 3, I use f of 2. Between 3 and 4, I use f of 3. Why the top left, not the top right, or why not something in between? The answer is it doesn't really matter. Because if I do the left versus doing the right, neither one is any better than the other. Some functions one might work better, the other might work better. And the real main idea is if I have enough rectangles, right, left, it doesn't really make a difference. Either way, my area is going to be pretty exact. So how does this show up in problems? This shows up in problems like so. Approximate this integral using a left Riemann approximation with two rectangles. So I'm approximating between, it doesn't even show it, -3 and 1. I'm approximating this area. And I'm approximating it with two rectangles. Two rectangles means they don't always have to be equally spaced rectangles. In this case, I'm going to do all equally spaced. If I'm going -3 to 1, that's 4 units I need to go with two rectangles. It means my first rectangle is going to go from -3 to -1, and it'll have a height of whatever it has to be to make it line up on its left side. This will be my first rectangle. And my second rectangle goes from -1 to 1, and it has a height of whatever it has to be to make it line up on the left side. Notice how both of my rectangles line up at their top left corner. This is the point -3, 9, and this is -1, 1. So I'm going to approximate this integral by just summing the area of the two rectangles. The orange rectangle has a width of 2 and height of 9. 9 because that's what I get if I plug -3 into the function, and that's the left side of the interval, -3 to -1. Plus the yellow area is, the rectangle is 2 wide and it's 1 tall. So it looks like the area of this rectangle is 18 plus 2, which is 20. If I have to approximate the area under the square root function, so I'm approximating area under the square root function from 1 to 10. Square root looks like this. And I'm approximating it with three rectangles. If I make them equally spaced, to get from 1 to 10 with 3 jumps, I'm going to have to go 1 to 4, 4 to 7, and 7 to 10. I approximate by thinking about 3 rectangles, each lining up with the left endpoint. So this rectangle looks like this. Between 4 and 7, I use f of 4. And between 7 and 10, I use f of 7. I can see that I have some area here that I'm missing. So I know if I sum up the rectangles, I'm going to get an under approximation, but I'll get something close enough. This will come out to area of the yellow rectangle. It's 3 wide, and its height is determined by f of 1. so square root of 1, plus the orange rectangle, which is 3 wide, plus its height is determined by f of 4, so its height is square root of 4, plus the area of the pink rectangle, which is 3 wide, and its height is determined by f of 7, so its height is square root of 7. This comes out to 16.937, and I actually ahead of time figured out what the actual area would be. That's our approximation. Our actual area is 20.415. So we have an under approximation like we expected, but we were close. Approximate the area under the graph of 1 over x. I'm adding my own words. The area under that graph between 2 and 22. So 2 and 22. And I'm breaking it up into 5 rectangles, going 20 forward on the x-axis in 5 steps, means each step I must be going 4. So I must go 2 to 6, and 6 to 10, and 10 to 14, and 14 to 18, and 18 to 22. And I've got a bunch of rectangles that all line up with the graph of 1 over x. And each rectangle has a height determined by the left point. So between 2 and 6, I use f of 2. Between 6 and 10, I use f of 6. Between 10 and 14, I do the height determined by the 10 end of it. Between 14 and 18, the height of my rectangle is determined by the 14 part of it. And between 18 and 22, it's going to look like that. The area of this approximation is going to be width of 4, height of my first rectangle has a width of 4 and a height of 1 over 2. My next rectangle has a width of 4 and a height of 1 over 6. My next rectangle has a width of 4 and with all these width of 4s, it'll be easier if I just write this as a 4 in front, and on the end I'll just distribute it into all the heights. A width of 4 times a height of 1 over 2 for this rectangle, 1 over 6 for that rectangle, 1 over 10, 1 over 14, 1 over 18. If I distribute in that 4 to everything, then everything becomes width times height. So this will make 3.575. I paused to make it sound like I was doing math, but I didn't. I paused the video, I went, got a calculator. It came out to 3.575. The actual area, the area under the actual function, comes out to 2.398. That's not great. It looks like my percent error is something like a 50% error, so not great. But if I had more rectangles, it would be fine. And a computer could approximate this very easily by using a lot of rectangles. Computers are good at doing a lot of simple math. Last problem is sometimes they won't give you the actual function. They'll give you a table of values. So here I'm using a table of values to estimate the integral from 2 to 10 of f of x dx. So between 2 and 10, I'm breaking it up into 4 rectangles. That's good because I'm only able to make 4 rectangles with this data. Those were random height rectangles, but when I draw it on my number line down here, I'm going to draw it a little bit better. Between 2 and 4, the height of my rectangle is going to be determined by f of 2, so it'll have a height of 17. It'll be a nice tall rectangle. Between 4 and 6, I use the height based on the left end of it for a left Riemann approximation. So I use f of 4, so only a height of 1. So while my first rectangle is 2 by 17, my second one is only 2 by 1. Between 6 and 8, I use a height of negative 2 because that's f of 6. So this is 2 by negative 2. And my last rectangle, between 8 and 10, I use f of 8. This rectangle has a width of 2 and a height of 8. So overall, this integral I'm going to approximate as being 2 times 17 plus 2 times 1. I'm just going to factor out the 2. I'm going to do 2 times 17 plus 2 times 1 plus 2 times negative 2 plus 2 times 8. So I'm doing 2 times 24, if I did my math right. I hope I did. Let's just check. It'll be embarrassing if I did. Yeah, that looks like 24. So it comes out to 48.